So in my last sentence there, I mentioned that a force could speed an object up, but why does that give it energy? It's because anything moving has something called kinetic energy, and you can just think of that as the energy of motion. The kinetic energy is going to be equal to 1/2 times the object's mass times whatever its speed is, and then you square the speed. There is an abbreviation here where it's EK for energy in the kinetic form or the kinetic type is equal to 1/2 mass times V squared. Just a reminder that the kinetic energy has to be positive because there's no way anything in here can be negative. And it also has to be a scalar, right? No directions. So as a quick example, how much kinetic energy does a 1,200 kilogram car have when it is traveling 26 meters per second on a highway? So let's grab the equation for kinetic energy and plug in our values. 1/2 times its mass times its speed squared. And we're going to plug everything in and then gather up the units. So typing it all into a calculator, I get 405,600. I had a kilogram, and I also had a meter squared divided by a second squared. So I have meter squared per second squared. But I'm guessing that this is supposed to be equal to a unit of a joule. So let's just do a quick unit conversion. So I can say that 1 joule is equal to 1 kilogram meter squared per second squared. And then these all cancel out with that, so I'm left with 405,600 joules. And then rounding that for just 2 sig figs, 410,000 joules. Earlier, I had also mentioned that work can be done by maybe lifting an object higher. And so how does lifting an object higher give it more energy? It's because another type of energy is called the gravitational potential energy. And we usually think of this as a stored energy just because of its height, just because of its position. And so this potential here, that word potential, basically just means stored. So objects that are higher up will have more gravitational potential energy, but it also depends on its weight. Like if you're going to drop a bowling ball from 1 meter up, that would have a lot more energy, a lot more ability to do something than if you dropped, say, a marble from 1 meter up. Right? So the weight matters as well. So I've just sketched out a floor here, and I've labeled that as 0 meters. So the floor here is going to be my origin. And I could imagine a shelf 1 meter up and a second shelf 2 meters up. And I can imagine, and I put a 2 kilogram brick on this shelf, a 2 kilogram brick, and a 1 kilogram brick. So of these three, which one would damage the floor the most if it were to fall? By instinct, I would choose this one. It's on the highest shelf, and for the objects on the highest shelf, it also has the largest mass. So I'm going to say that this one has the most stored energy, and if it were to fall, would have the most ability to break something or damage something. So let's just quick take this one block and find its gravitational potential energy. So our equation is going to be the gravitational potential energy is equal to the weight times the height of the object. The weight here is going to just be found by doing m times g, and then we multiply by the height. So I should maybe put this equation in a box. So here's a nice abbreviation for it. The energy in the potential form is equal to mgh. So if we're going to plug in our numbers for that one brick, we plug in the mass of 2 kilograms, plug in g, and plug in its height compared to our origin, which I called the floor, which was 2 meters. Doing the math, I get 39.2. Gathering up the units, I get a kilogram meter squared, because they're multiplied together, divided by a second squared. But this is also equal to a joule. So instead of saying all that, I could just say joules. Let's do an example where we tie the idea of gravitational potential energy to work. So let's imagine a 500-gram book, and it's going to be lowered 50 centimeters. What is its change of energy? And also, what is its work? So we could find the work by doing Force times distance, that's one way to do it. But first let's answer that question, what is its change of energy? So the change of energy is going to be the final amount minus the initial amount. And so the final energy was just this gravitational potential energy, and then we'll subtract off the energy it had initially, which was just the gravitational potential. So we can do mass times g times h, and I put a little f in here for final, the final height, minus mass times g times h, but I left a little I here for initial height. To shorten it up a little bit, I just factored the m and the g out in front. My initial position was higher, and my final position was lower, and it had gone downwards. But where is my y equals 0? So I'm going to say here that my height is equal to 0. And really, you could kind of pick whatever you wanted. Your height could be whatever you want here. But whatever it is up here, it has to be 50 centimeters more. So since my height was 0 here, my height here has to be 50 centimeters, which is also 0.5 meters. So then my final height was 0 minus my initial height. My initial height was 0.5 meters. So I end up with a negative value, a negative 2.45 kilogram meter squared per second squared. Is it possible to have a negative change in energy? And the answer is yes. That just means energy was removed. It lost some of its gravitational potential energy. So rewriting kilogram meter squared per second squared as a joule and rounding for sig figs, I end up with just negative 2 joules. And that was its change of energy. What was its work? Well, work is, by definition, the amount of change of energy done by a force. Well, this was the gravitational force that was pulling on it during this change. So the work is also just negative 2 joules. The work is the change in energy. For section 3, which is conservation of energy, it basically means that energy can transfer to different types. Like right now I might have potential energy, but I could change that into maybe kinetic energy. Right now I have chemical energy. Later on I could climb some stairs and then I would have gravitational potential energy. Energy can change forms. And you can also change it to other objects. You can get energy from a different object, like when you eat food, or you can give energy to another object, like when you lift it up. But energy as a quantity cannot be created or destroyed. Now, this section in your book went into a lot of detail, and unfortunately, I think that too much detail might be confusing with this. And if we're not going to really dig into all the details, let's just give you one example and how we can use this. And let's just look at it for a simplified case where we're only going to be considering kinetic energies and gravitational potential energies for a single object. So for our simplified case, let's just imagine an object is going to drop. And as it loses height, it's going to lose gravitational potential energy. The lost gravitational potential energy, it can't just be destroyed, it has to go somewhere else. So in our simplified case, it is going to become the energy of motion, kinetic energy. So what we're going to do is we're going to apply the idea of conservation of energy to the situation. And conservation in physics really just means the initial amount of something is equal to the final amount of something. So in our simplified case, the initial amount of total energy has to be equal to the final amount of total energy. So here I wrote that out in a different way. So far, we've only covered kinetic and potential energies. And whenever we are just considering kinetic and potentials together, we often just bundle them together and call them a mechanical energy. Your book will use that term a few times. I teach it to you mostly so you can understand your book. All right, so let me sketch this out as a little bit of a diagram. Initially, I can imagine the ball up higher. And let's say it was dropped, and so it was at rest from a height of 3 meters. And we'll imagine that as being speed of 0 right when it was dropped. And then we'll imagine it at a final time. And this is going to just be about to hit. So that way we can study the kinetic energy it has just before it hits. And so right before it hits the ground, we can also just say that the height is 0. but it will have a velocity. So initially, did it have any kinetic energy? For our example, no, it didn't, because it was at rest. So we can even just get rid of that for this example. Did it have potential energy, the ability to fall? Yes. Now what about final? At the final point, did it have kinetic energy, energy of motion? Yes, it was moving. Did it have gravitational potential energy, any more height that it could fall? And the answer is going to be no. So we can even just get rid of that right now. So the initial amount of gravitational potential energy is going to have to be equal to the final amount of kinetic energy. So just kind of rewriting it this way, there's my initial gravitational potential energy is equal to or conserved with the final kinetic energy. So how about we use this idea and this equation then to solve for something? One thing we could solve for is how fast was it going just before it hit? So let's find this v here. So let's first rearrange this equation to solve for v. All right, so I rewrite my equation. Trying to solve for vf, I'm going to multiply 2 to both sides. So that way my 1/2 will cancel. And I'm going to divide both sides by m. And so this m cancels off that side and this one. So then just rewriting it, I have 2ghi is basically just equal to the final speed squared. But if I just want to know the final speed, I should take the square root of both sides. So then the final speed is going to be equal to the square root of 2 times g times the initial height. Plug in all your numbers, type on a calculator, and I ended up with 58.8 meters squared per second squared, and all of that is under a square root. I did the square root of the number and got 7.668, and I also did the square root of the unit and just got meters per second. Rounding for sig figs, 8 meters per second. Since this was a question about how fast it was going, that to me implies speed, so I don't need to give this a direction. If it had said what is the velocity it was going, you would need to add the word down just to make it a true velocity.